I'm going to use the next 2 lectures to talk about input regularization or input binning, and then I'll talk about compaction, how we deal with sparse data structures and regularizing difficult data distributions and so on. So that should give you a sense of how to apply some of these tiling and coarsening techniques to even more challenging applications. And from my experience at that point, it should be a very good entry point for you to deal with pretty much all the PDE applications and the embodied types of applications. So one interesting problem with parallel computing through history is what we call the data scalability problem. And essentially when we convert a computation from scatter-based approach to gather-based approach, we oftentimes run into a problem with efficient identification of input data relevant to each output. So oftentimes these parallel algorithms end up having to look at more data than the sequential algorithm. And at that point, you can actually expect when the data set becomes very big, then the computation can actually become slower than sequential. And this is a classical problem with many parallel algorithms, and we call it data scalability problem. So input binning is actually a very frequently used technique to allow you to solve that problem. Bring a parallel algorithm's data scalability back up to into a more efficient algorithm domain. So I'd like to also give you some sense about what the common trade-offs are in input binning. So just quickly, we have talked about transforming the scatter-based approach to gather-based approach, right? So when you are in the gather-based approach, the most important issue is to efficiently figure out what are the input data subsets that are relevant to each output. Right here. So the problem is the input tend to be much, much less regular than output. And oftentimes, when you have some kind of large-scale measurement or large-scale models in your scientific computing or engineering computing, input tend to be what you get from the real world. Signals that you sense and molecular atom structures and all those things are very irregular. So it may be difficult for each thread to efficiently locate all the input relevant to its output, or to efficiently exclude all the input irrelevant to its output. So in a naive approach, in fact, it's not so naive. If you look back into the literature, a lot of the parallel algorithms actually have this problem. And so it's not that people are stupid. It's actually something that is a very easy to fall into as a pitfall. So in a naive arrangement, all the threads may have to process all the inputs. You may need to actually just go in and look at the input just to determine whether you need to process it or not. But in those algorithms, if you're not careful, you can easily take your complexity and blow it up because you ended up looking at all the inputs. And this makes the execution time scale poorly with data size. It's especially a problem for parallel processing because usually the reason why you go into parallel processing is because you have large input data set. And if you have a very small input data set, you may as well just run a sequential code and it will run fast enough anyway. So when the combination of large data set that are typical for parallel processing and this kind of problem would make many of these parallel algorithms unusable. So let's go back to the direct Coulomb summation algorithm. I promise you I come back to this this problem 2 days ago, but so this is where we are. And remember we have these energy potential points, and we have these atoms. So at each grid point, we want to sum the contribution of these atoms to the grid point. It's highly data parallel, but it has a quadratic complexity. That is, the amount of computation is proportional to the number of grid points multiplied by the number of atoms. And when you have a large volume to simulate, both are proportional to the volume, right? The bigger the volume, the more the lattice points. And the bigger the volume, the more atoms you're going to have. So it becomes n squared, n where n is the volume, the measure of the value. So this gives you very poor data scalability in top volume. And how bad can that be? It can be this bad. That is, this is a real measurement using VMD implementation. And when you are simulating, larger and larger volume, this is a log scale plot. And these top two lines are the direct Coulomb summation implementation using the GPU, and the sequential, the best CPU sequential implementation using SSE. And you can see that for very, very small volume, there's just not enough to keep the GPU busy, so the CPU is faster. And there's a pretty good range of volume where the GPU actually does very well. Okay, it has substantial performance improvement over CPU. Remember, this is a log plot, so this is actually quite a bit of speed up. But when you have large enough data, that quadratic complexity of the algorithm starts to take effect, and the CPU's scatter-based approach start to prevail. Okay, so this is the classical situation where when the data set gets big enough, a lot of the parallel algorithms start to run slower than the sequential algorithm. Okay, and what I'm going to talk about today is a set of binning techniques that allow you to efficiently resolve this problem, so that your execution is actually going to be consistently faster than both the CPU execution and the direct Coulomb summation parallel execution, and it maintains a good scalability all the way through. Okay, so that's what the binning techniques are for. The algorithm for the key to both sequential and parallel efficiency is this concept of cutoff. A lot of the physical phenomena can be approximated if, let's say, certain things are far away enough, then the effect on the grid points, it can be very small, and you can ignore it. And I was going to say something like, well, if you have a earthquake in Chile, the effect on Japan can be very small, but sometimes you cannot totally ignore that, right? So you need to be careful with these things. So for this particular Coulombic summation algorithm, once the distance goes beyond a certain point, you can start to ignore the effect of these atoms on the grid points. So for bio type of simulation, typically the cutoff point, the distance is between 8 angstrom and 12 angstrom. And this is a domain kind of decision. And so if you are processing different kind of scientific data, you need to use your own domain to determine the cutoff distance. So the number of atoms within the cutoff distance is roughly constant, because whenever you have a fixed cutoff distance, you have a fixed volume of atoms that can affect each grid point. And in any kind of solvent or any kind of material, you tend to have a somewhat uniform distribution of these atoms and so on. That the typical simulation that people use NAMD to simulate, that means that the cutoff distance will include somewhere between 200 and 700 atoms. But the point is bounded. Okay, so now all the input that each grid point needs to look at is bounded by a some kind of constant. And that constant drops the complexity of the entire algorithm down from n squared algorithm to n algorithm. Okay, so that's where the scalability comes in for both sequential code and parallel code. The summation formula looks like this, and you have a smoothing function to make sure that all the atoms that are close enough to the cutoff points are somewhat tapered a little bit, so that you don't get numerical instability. But you probably understand these things more than I do. So the implementation challenge is that if you use output-oriented programming, such as the gather-based approach, how do you efficiently find all the atoms that are within your cutoff distance? Okay, so that now it should become very clear, what are the things that we need to accomplish. This is part of the reason why the sequential implementations tend to use scatter-based approach historically, because it's just very easy to just take a look at the input and then find all the output points that should be affected. However, if you look at the most modern code for the high-performance CPUs, even the sequential code has become scatter-based approach for cache locality reasons. So if you look at the sequential code, they actually use the same type of binning technique as I'm going to be talking about for parallel code. Okay. So what is binning? Binning is really a process that groups data to form the chunks called bins. So you spend some little bit overhead up front. Look at your input data. Look into all the coordinates of the atoms, and then essentially sort them into these groups. And each group corresponds to some kind of neighborhood of coordinates. Okay, and this is overhead. You're doing this pass before the real computation. Binning could be done sequentially, and there are also parallel algorithms for binning. So you could do binning on the CPU, you could do binning on the GPU. So what I'm going to do is I'm going to talk about a CPU-based binning algorithm in the morning, and I'm going to talk about a GPU-based binning algorithm in the afternoon, assuming that we have enough time, okay? And then one of the things that many of you should also keep in mind is that binning is, a fairly general concept that comes in many shapes and forms. It all has to do with how you pre-scan your data and make some arrangement that you can execute the code more efficiently later on. And a very frequent way of binning is uniform distribution, but it's not the only kind. There are also binning algorithms where you will partition your space in a non-uniform way, such as what we call the KD trees and quad trees and so on. Many of the people in the astronomy would know these terminologies. And those partitions are actually still binning algorithms, because you're trying to partition your space into non-uniform ways, but each bin will contain roughly the same number of inputs. So it's all about somehow regulating your input into these groups that are of comparable numbers, okay? And if the data distribution is highly non-uniform, your partition may become very non-uniform. And a lot of the techniques that I talk about today will be also applicable to KD trees based algorithms and so on, okay? So let's go into a uniform binning approach, and it's probably conceptually the simplest one, and hopefully we can finish by 12:30. And so the binning for this cutoff potential can be easily done by partitioning your space into equal-sized partitions. And so within each partition, you can collect all the atoms that fall into that little volume, okay? And you can probably expect that if you can collect all these atoms into a group, then for any grid point, you can use its physical coordinate to figure out which group or which groups that the output should be looking at. So by doing a little bit pre-arrangement, you actually take the atoms which have implicit internal representation of the coordinates. But then once you produce them into groups, those groups will have coordinates that allow you to quickly calculate from an output point to the coordinate of these groups that should be looked at. Make sense? Okay? And so that's why it's very important that after the binning, every cube has a unique index that can be quickly associated from a output point coordinate to the input group coordinate. And binning is really what we call the spatial sorting technique. And it actually sorts atoms into two different groups. And during computation, they actually appear as three different groups. So for a particular output point, there is a quick way to determine if one of the groups or multiple of these groups have promising inputs that should be considered. So any input points that are outside the binning, the relevant binning groups will not be looked at all. However, within the group, within those bins that are looked at, if you draw the distance, some of the atoms are still going to be outside the cutoff distance. So even when you look at these bins, you still need to screen away some of these atoms that shouldn't be used for the actual computation. So some people call binning an input coarsening technique. And the reason is you are actually taking these fine inputs and then coarsen them into these groups that you will be looking at these groups all together, but use the condition statement to screen them away. Okay, so that's why sometimes you would hear people saying that this is an input coarsening technique. There are two things that I'm going to use, and it can be somewhat confusing, so I want to make sure that we cover it first. One is the bin size. Bin size typically refers to the physical volume covered by a bin. Okay, so when you think about your simulation model, you can think about the physical partitioning, okay, of your space, and how big each bin will cover is called the bin size here. Whereas the bin capacity is the internal representation, and it has to do with how large an array you allocate to accommodate all the input atoms for that bin. So you could, the larger the volume, you probably should have the larger the capacity, right? But it's not always the same. Okay, so that's why these two are actually independent parameters that can be tweaked, and oftentimes we actually tweak the capacity in order to reduce load balancing problems. Okay, so that's why I want to make sure that we set it up first, and then we'll talk about that. So there are a couple of things that you should think about. One is for bin capacity. These atoms need to, the capacity of these atom bins need to be balanced between two different conflicting requirements. One is if the bin capacity is too large, then you'll end up with many dummy atoms in the bins, okay? And this will cause some problems, and you're going to see some, see some implementation, and you're going to see exactly where those problems start to pop up. And the second one is if the bin capacities are too small, then some of the atoms will not fit into bins. You need to figure out where they go. Okay, you need to figure out how to take care of those. So the target bin capacity should cover more than 95% of the atoms. And this is assuming that all the excess atoms that cannot fit into bins will be thrown into a excess or overflow bin that will be processed by the CPU. Okay? So this assumes that the GPU will get about 20 times speed up over the CPU, so that if you put 5% of your total input into a CPU overflow bin, the computation time on both sides will be roughly equal. Okay, so that you can totally overlap the computation of the CPU and the GPU. This is the reason why NAMD type of program are very good examples of joint CPU and GPU computation. If you look at most of the calculation phases that use GPUs in NAMD, there's almost always a component of some kind of overflow stuff that goes into the CPU, and they actually fully utilize the CPU, and it's parameterized. So depending on the speed up that you get, they will get sent more or less to the CPU and balance the balance the time. So we're going to be talking about uniform size, uniform capacity bins, which allows very simple array implementation. And we can just use relative offset approach to actually get high computation efficiency. However, these approaches can be very wasteful when your data distribution, where your input, like atom distribution, are non-uniform, highly skewed in some way. So that's why in the afternoon we're going to be talking about compaction, okay, how we compact these things and get more efficiency. The bin capacity could be should be large enough to contain all the atoms that fall into a bin, or as 95%. So then the cutoff will screen away the atoms that weren't processed. So the kernel code, within the kernel code, you should still expect to see a if then else that screen away some of these things. And sometimes it's not very easy to calculate the cutoff distance. So I'm actually going to show you in practice how Johnstone does it in VMD, and it may be applicable to most of these other applications as well. And the performance penalty, arises if too many are screened away. That is, if you have a bin structure where each thread needs to look at a lot of atoms that are actually outside of the cutoff distance, then you have lower and lower computation efficiency, right? So that is going to be a very major factor, and you may be surprised about the computational efficiency of some of these implementations. So I'm going to show you some numbers. I was a little surprised when I first saw some of these numbers. So going from so if you think about binning, one of the very common situation is you may have a direct summation style kernel where all the inputs affect all the outputs, okay? And then you say, what's the minimal amount of work I need to do in order to make that kernel work with a binning approach, okay? So, what's the minimum of work I can do in order to make my computation scalable, data scalable? So I'm going to talk about the large bin approach that allows you to quickly convert your direct summation style kernel into a bin kernel. It's not the best performing kernel, but it can actually give you substantial improvement over the total direct approach. So the adaptation of these from the direct kernel can be is very straightforward. Atoms are actually stored in the constant memory, with the DCS kernel, and the CPU will loop over a potential map regions that are about 24 angstrom cube in the VMD example. So these things are relatively big. Remember the cutoff distance in this particular case is between 8 and 16 angstrom, right? So these regions are actually bigger than the cutoff distance. So it's relatively big, 24 angstroms cube in the volume. So these are the physical bin areas, okay? Now, so each map region requires only one large bin of items. So you take this region and then you generate a bin that is actually even bigger than that region, so that you cover cover all the atoms that should be examined. So you just then the atoms are in the corresponding large bin are appended to the constant memory. So essentially, you will take all the inputs in the bin that should be looked at, okay, and just continue to insert all those atoms into constant memory until the constant memory is full, because the constant memory can only take 64K bytes. And as soon as it's full, you launch a kernel. Okay, you launch a kernel, and that kernel will calculate all the lattice points within the 24 angstrom cube. Okay. And this is designed to be large enough for you to have enough threads to justify the launch of that kernel and to fully utilize the GPU. So in a large bin kernel, when you send a single volume to the GPU, you need to make sure that there are enough lattice points and so on that can really fully justify the execution. So for each map region, and then the host will actually continue to reload constant memory when the kernel finishes and launch the GPU kernels again until all the atoms in the corresponding large bin are consumed. And then it will go back and look and pick up another volume of lattice points, send it over to the GPU, and execute. Okay, so the kernel itself in this kind of strategy is identical. The structure is identical to the direct summation kernel because remember we're sending over a big chunk, okay, a big chunk of bin, right? A big bin. So for that single bin, all the input should be considered for all the lattice points. So when the threads can simply just say, I'm going to scan through all the inputs of this bin. Okay, I'm going to scan through all the inputs of the bin, and then I'm going to just use if then else to screen away the ones that I'm not supposed to use. So this is not ideal because you can imagine when you have such a big bin and such a big volume, not all the lattice points are in the same, are even close to each other in the physical location. So many of them will be looking at atoms that are just very far away, right? However, this at least allows you to cut away a huge number of inputs outside that big bin. Okay, there's still, it's still much, much smaller than the entire space. So that's where you get the benefit, okay? So the map, a couple quick calculations. So if we use 24 angstrom cube in the volume, that means that for half an angstrom grid spacing, which is typical what they use, this means you're calculating 48 lattice points cube in your kernel, which is a lot of lattice points. So that keeps the GPU busy. And if you assume that there is about one atom per angstroms cube distribution, then we're talking about somewhere around 20 atoms cube on average in each large bin. So this is about 8,000 atoms. And that actually fits probably into 2 constant memory batches. Okay, if you calculate all the coordinates and weight and charges and so on that you need to represent for these atoms. So the bin size and capacity are designed to allow each kernel launch to cover enough lattice points and to justify the kernel launch overhead and fully utilize the GPU hardware. Okay, so that's what it is. And this is truly a easy adaptation of the kernel. If you take the original DCS kernel code and you add this little if then else, and you're pretty much there. Okay, so that's why it's something that if it works for you, you should just try. For this large bin cutoff kernel, in general, it runs about 6 times over the fastest CPU version. Okay. So, it's still well worth it because, even though you will end up looking at a lot of atoms that probably shouldn't be looked at, and the efficiency is only about 6.5%. That is, for every thread, when the thread looks at 100 atoms, only 6.5 of those atoms are actually used on average to affect the output grid point of that thread. Okay, so this is definitely something that you can further improve. Okay, however, the further improvement would require you to do more sophisticated kernel code. Okay, so I'm going to spend the next few minutes talking about how you can design smaller bins and achieve higher efficiency and better execution performance. Okay. So the concept of the small bin kernels is that each thread block you're going to actually use smaller volumes of lattice points, And you're also going to be generating small volumes of bins. Okay, so both are going to be reduced. And each thread block will now process a small cube, okay, a small cube of this of these lattice points. Okay, so each thread block will examine the atom bins. So, but when you have such a small bin, then the cutoff distance can actually be bigger than what's covered by a bin, right? Remember, the big bin was actually big enough that it covers the cutoff distance, right? But here, now that we have much smaller bins, there could be multiple a number of small bins within the cutoff distance. So the trick is to figure out how to allow each thread block to look at a minimal number of bins and quickly identify what they are, okay, and without a huge overhead, okay, because the calculation of these indices could be very expensive. Okay, these are Euclidean distances and coordinate transformations. So you don't want to spend a whole lot of overhead just to be able to identify those those bins that need to be considered. And what we do here is we use a sphere of bins to calculate by each thread block to calculate a small cube of lattice values. And so all the threads in that block will look at all the bins, okay, all the bins that in the collection. And there's no hardware penalty for multiple simultaneous reads to the same address. So what this means is that if you have enough threads in your cube, then every bin that you read from the memory will be reused multiple times. All the atoms in the bin will be reused multiple times, one by each of the thread lattice points. Okay, so this is a very good tiling algorithm because the tiles are those bins, and whenever you load those bins, the threads in a block can all consume the same bin many times. In this case, I'll show you it's about 128 times. And that's the reason why a lot of the VMD algorithms are not memory bound, because they, essentially they took away, they reuse the memory content so efficiently that they don't need to be, it does not impose any bottleneck. So the sphere is to be big enough to cover all the grid points at corners. That is, you may have situations where you have some of these grid points that are on the outside edge of that little volume. So in this particular case, an atom A in this bin will be within distance of n, but outside the distance of m. So you need to make sure that the sphere is big enough that it covers all the atoms for n. And you will need to, in general, cover a bigger sphere than if you only consider individual lattice points. Okay, so these corner lattice points are the troublemakers, right? They require you to stretch out your sphere. Okay, but that's regularization. Remember the wedding banquet? You can't really ask them to customize food for you when you have 1,000 people. Here, when you have so many threads, if you want to have SPMD execution, you need to regularize your data so that it's big enough to cover the needs for everyone. Okay, and then each one will have a little bit of waste. Okay. Have you ever wondered when they serve the airline food? They give you, everything: salt, pepper, butter, cheese. It doesn't matter if you want it or not, right? And have you ever wondered what happened to all the things you didn't eat?
They serve it the next week, I think, right?
Probably. That's regularization. Okay, so there'll be a small level of divergence because because of this kind of phenomena, right? Okay, so 5 more minutes. I think I can get somewhere in 5 minutes. So I showed you all the pictures as this kind of little circle. But in reality, what you really have is you have a volume of lattice points, and then you have a volume of bins, right? All these are, these are collection of those small bins. So essentially the problem is to represent all these volumes in terms of their little volumes in terms of their coordinates that all the threads in this block need to examine, right? So that's the little trick. And this is called the neighborhood for that thread block. So the most efficient way that we know is called the neighborhood offset list. And basically, once the simulation, once you launch something like a BMD, you will know all the grid spacing, and all the user will tell you all these things. When they launch the ion placement function, and then so based on all the parameters given by the user, then BMD will actually calculate all the grid spacing, okay, and decide all the bin sizes and so on, and then calculate for a generic volume all the offset, the XYZ offset of all the bins that need to be examined. Okay, so it can be a very long list. Okay, but the list actually gives you all the XYZ offsets of the bin coordinates that of all the bins that need to be looked at. So this list is given to the GPU. Okay, and this is calculated on a relative basis. So it doesn't matter where the thread block is processing. It only just takes its own coordinate and then add all these each of these offsets to identify the coordinates of the bins that need to be examined. So that's why it's a generic list. It can be used by all the thread blocks. Okay, and so by visiting the bins in the neighborhood offset list, you can iterate through all the atoms. So the algorithm, now you should probably see how the algorithm works. When you write a piece of kernel, the kernel is going to be looping through the neighbor list, and for each bin in the neighbor list, you will load all the atoms in that bin into shared memory, and everyone will look at the atom and determine whether the atom should contribute or not contribute to its lattice point, and then move on, right? So this is actually probably not, oh yeah, this is just a review of the large bin. And now, oh, I should have eliminated all that stuff. Done, done, done. Okay. So the pseudocode looks exactly like that. For each atom in the simulation volume, the CPU will assign them into these bins. Okay, so this is a CPU binning algorithm. It's a single pass through all the inputs, and then you would assign, you would generate all these bins, and then you would generate a neighborhood list, offset list. So you would take a volume, a big volume, and then test whether a three-dimensional square, it's a square volume, yeah, square volume, cube volume, has whether each bin in that volume should be included or not included in the offset list. Essentially, you're screening away those corner bins, right, from the cube volume, and then it hands over this to the GPU. So essentially, in this case, it's no longer sending one bin at a time to the GPU, but it's actually sending a pretty big volume, okay, pretty much the entire volume that can fit into the GPU memory, because the way you should think about it now is that the entire volume of, of the lattice point is going to be on the GPU, and you have multiple of these thread blocks, okay, multiple thread blocks that are all running. And each thread block is going to look into a window of that volume. Okay, so they all have their offset list. So they're all taking their coordinate. They're all indexing into a subset of the GPU memory. And they are all going to be screening away the ones that are not supposed to contribute. Okay, so that's that's this particular part. Okay. Performance. This is a order m times n prime algorithm, where m prime is the number of the m's is the number of output points, and n prime is the atoms in a neighborhood volume, in the neighborhood, right? And that neighborhood is bounded. So that's why it's still a linear algorithm. And then it works well if the distribution of atom is uniform. So this afternoon, when we come back, I'm going to give you another additional insight into some details of the small bin design, and then we transition into compaction, and what happens when the input distribution is not uniform, and how that relates to the sparse matrix techniques. So hopefully we'll have enough time to cover both, and then I'll give you a quick summary of what else you need to know when you move forward. Okay? So I will see you this afternoon. Thank you.